video, I would like to discuss the basic concept of conditional probability, independent and dependent event. So the first simple example, I would like to flip a fair coin twice. So what is a fair coin? A fair coin means the coin is not manipulated. So the probability of getting a head is 1/2. The probability of getting a tail is 1/2. So you flip a coin twice. So what is the probability that the first coin is a head? So first coin, consider the first result. So probability, you have a first head, right? So first head is 1/2. Now, how about this? We have a 1/2. So if you flip the coin again, the probability to get a head is also 1/2, right? My second question is, what is the probability that the second coin is a head given the first coin is a head? So this is what I'm going to write. I am looking for a second head given that the first coin. So the given, I would like to write this word out, given that the first coin is a head. So here is what happened. Picture this in your mind. You have one coin. You flip the coin. That is your first flip, right? You flip a coin. You get a head. The probability is 1/2, right? Now you already have a head. Pick up the same coin. Flip the coin again. What is the probability that you will get another head? Is 1/2, right? So it's always 1/2. So another way to say this, the coin is memoryless. So the coin is memoryless. So that means every time you pick it up, flip it, the probability to get a head is always 1/2. The coin is completely memoryless. So the first result is a head. That doesn't improve the probability to get a head in the second result. So every time you flip it, the probability to get a head is 1/2. So in this problem, I have two events, the first head and the second half. So since the second event doesn't affect, since the first probability, so since this 1/2 does not affect this 1/2, then we say that these two events are independent. So two events are independent. So this word independent, they are independent events because the first result doesn't affect the second result. So that brings me to the definition of independent and dependent event. It's very simple. Think about this. What is the definition of independent? Independent means you have two items, one doesn't affect the other. So let's say you have two people, they don't affect each other, so they are independent, right? They don't affect each other at all. So that is the definition of independent. So two events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. So one doesn't affect the other, we call them independent. If two or more events are not independent, then they are dependent. So the independent and dependent, they are like one side or the other. Two events, they are either independent or dependent. They either affect each other or they don't affect each other, right? So that is independent and dependent events. So I have an example right here. There are 6 red balls and 4 blue balls in a box. You choose 2 balls randomly, one at a time. Calculate the following probabilities. So the first one is, so let's draw a picture. I have a box, so this is my box. I have 4 red and then 6 red and then 4 blue. The total is 10, right? So I select 2 balls, one at a time. So number 1 is the first ball is blue. So probability, first blue. Why don't we say 1B? The first ball is blue. So the total frequency is 10. There are 4 blue balls, right? Okay, so we turn the blue ball back to the box. So now you got a blue ball, right? You put it back to the box. This is very easy to picture in your mind. You have a box, 6 red, 4 blue. You take one out, that is a blue, right? You record it. The first result is a blue. Now you put it back. Okay, so put the ball back. Okay, the second ball is blue. Okay, so now I am looking for the second ball is blue, but given the first result already occurred, right? The first one is blue. So what is the probability? The probability is still 4/10. All right, so let's take a look at number 2. So number 2, the first ball is blue. All right, we just did it. So the first ball is blue. So that is 4/10. So now here is the difference. You hold on to the first ball. This time you don't put it back. Now you select a second ball. So probability, what is the probability? The second ball is blue given that the first ball is blue. What if you don't put it back to the box? So if you don't put it back to the box, that changes the total. So this is no longer 10. The total is 10 minus 1 because you are holding the first ball. How many blue balls do you have in the box? So there are 4. You are holding 1, so there are 3. So that will be a 4 minus 1. So the second blue, so this is 3 divided by 9. So if you don't put the first back to the box, that affects the probability of the second blue. So in here, number 1, the first blue and second blue, they are independent, right? Because these two events, they don't affect each other. But in number 2, if you don't put the ball back to the box, that affects the total. So the first probability affects the second probability. That means we say that these two events are dependent. The second blue ball, that probability, these 3/9, depends on the result of the first probability. So since they affect each other, then they are dependent events. All right. So the next page, we have some probability rules. So let's just bring this up. So multiplication rule for independent event, if two events A and B are independent, then we have probability of A and B equals to probability of A times probability of B. In some textbook, they do this. So probability, instead of writing A and B, they do A, this one is intersect B. It's like upside down U. So that is equals to PA times the probability of PB. So in some textbook, they use this symbol. This symbol means N. N means intersection. All right, and then we have one more, conditional probability. A conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of event B occurring given that A has occurred is denoted by this. So this is the probability. You are looking for the probability of B given. This long bar means given. Given means I already know A. I already know A I already know what A is. Now tell me B. So there are two formulas. If you are looking for B given A, then that is B and A divided by probability of A. If you are looking for probability of A given that B has already occurred, that is equals to A and B divided by the probability of B. All right. So these are two probability rules for conditional probability. So some textbook, they don't put it in that way. Some textbook, they will just multiply both sides by the denominator. So they go from here to here. The concept is simple. So let's say you have 6 equals to, don't use 6. How about this? You have 2 equals to 6 divided by 3. If you multiply 3 on both sides, then you have 2 times 3 equals to 6. So if you multiply the first one, if you multiply PA on both sides, then you have the conditional probability times PA equals to B given A. So on the other hand, if you multiply PB on both sides, so let's say you have a 10 divided by 2 equals to 5. You multiply 2 on both sides, then 5 times 2 is equals to 10. Now, I know what you are thinking. You are thinking about, hey, no. Hold on. I just saw something on the previous page. Hey, you have A and B equals to PA times PB, right? I have this multiplication right here. Then the question that you are thinking right now is, hey, look at this conditional probability formula. In the numerator, we have B and A and B. All right, so why don't you simplify this? Why don't you put the probability of B and A, you rewrite that as the probability of B times the probability of A. And then this probability of A cancels the probability of A in the denominator. Why don't you simplify the formula? This is not in the simplest form. So let me tell you why. You can only do this if you have a solid evidence to prove that A and B or B and A are independent. In order to put the N as a product, you must show that they are independent. You need an evidence. Without this evidence, then B and A is just B and A. Again, if you are not able to show that they are independent, the A and B, then A and B remains as A and B. There is no way to rewrite it as a product. B and A remain as B and A. There is no way to rewrite them as a product if you do not have evidence to show that they are independent. All right? Now, what if they are independent? So let's say two events are independent, right? So one doesn't affect the other. Then this conditional probability becomes the probability of B and A is just equals to B. So not B and A, sorry. B given A is just equals to B. A given B is just equals to A. So let me give you a quick proof right now. So we start with the probability of B given A. So using the formula that is B and A divided by the probability of A, right? I just said that they are independent. I just gave you this evidence. So you are able to write the B and A as B times the probability of A, and then divided by probability of A, and then you cancel the A, that is equals to the probability of B. If you want an easier math to understand, if you want some easy maths, let's say 2 times 5 divided by 5, you can get rid of this 5. The answer is equals to 2. Or you multiply 2 and 5 equals to 10, and then 10 divided by 5 equals to 2. So B given A is just equals to B. So this is a mathematical proof. What about a non-mathematical explanation? What is B? What is this? This is B given A, right? You already know A. Under this condition, you want to find B. Since A and B are independent, all right, you just say A and B are independent. That means A doesn't affect B, B doesn't affect A. All right, so that tells me in order to find B, I don't need A at all. Why do you need to give me A, right? Because they are independent. A doesn't affect B. So to find B, I will just go ahead to find what B is, right? I don't need the A anymore because they are independent. If you want to find B, you go ahead and find B for me. A doesn't affect B, why do you need to give me that piece of evidence? How about this? The probability of A given B, they are independent. B doesn't affect A. If you want to find the probability of A, you go ahead to find the probability of A. All right? You don't need B anymore. You don't need B at all because they are independent. B doesn't affect A. So if you want to find A, then you go ahead, find A. All right? But going back to this conditional probability formulas, again, if you want to break the A and B as a product, check the problem really carefully. Did they say that those two events are independent? If they didn't say so, then do not break it down as a product. All right? Now, let's do exercise. This one. 2 fair dice are rolled. Find the following probability. So let's do the sample space really quick. So 2 fair dice, right? It can be 2 faces. The smallest is 1 1. The biggest is 6 6. So we have 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. This is not a 16. All right. 1 6 means the first die is a 1. The second die is a 6. So it can be a 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. 3 1, 3 2, 3 3, 3 4, 3 5, 3 6, 4 1, 5 1, 6 1, and then I fill up the rest. 4 4, 4 5, 4 6, 5 2, 5 3, 4 5 6, 6 2, 6 3, 6 4, 6 5, and 6 6. There are 36 outcomes. A is the probability the first die is a 5. How about this? First one is a 5. Okay, you roll the first die, you get a 5, so there are 6 faces. 5 is one of the 6 faces, so that will be 1 out of 6. If you consider the second die only, probability of 5, no, not 5, second 5. So that is part B, that is also 1 out of 6 if you consider each die individually. And then C, the probability to get a 5 on the first die given the fact that the first die is a 5. Okay, so probability, you already know that the first die is a 5. You are looking for probability that the second die is a 5. What is the probability? The first die is a 5, right? The second die is a 5. Does that affect the does the first die affect the second die? You roll a first die, you see a 5. So now this first die is the 5 is facing up. Done, right? And then you pick up a second die, roll the second die. The second die gives you a 5. Does the first die, the one on the already on the table, the one that is already on the table, affect the second die? No. So this is still a 1/6. All right. And then D, the probability getting a 5 on the first die and a 5 on the second die. So this one, the first and the second, they are independent, right? It doesn't matter how many times you roll it. Every time you want to get a 5, is always 1/6. So they are independent. All right. So here is how I explain that. So let's say that is A, that is B, then this is B given A. So since they are independent, then the probability of B given A is just equals to the probability of B. So they are independent, then D, the probability to get a 5 on the first die and a 5 on the second die. So probability of first one is a 5 and the second one is a 5. Two events are independent. How do you find the n? A and B, that is equals to probability of A times the probability of B, right? When they are independent. Okay, so the first die is a 5, that is a 1/6, and then times 1/6, so that is equals to 1 out of 36. So that is first 5 and a second 5. So that is using the probability formula to find the n. Now, look at the sample space. Can you prove that the answer is 1/36? Just use the sample space. Look at the sample space. How many outcomes do we have? 36. Which one is first 5 and second 5? There is only one. So this is 1 out of 36. So this one, I use a sample space to find the answer. This one, I use a probability formula to find the answer. Which one is better? This one is better. What if the sample space is big? It's hard to get all the outcomes out. Then you will have to use the probability formulas. All right. So that is the first example. So let's take a look at the next one. So the next one, let's put this up. Defective product. There are 100. This is a typo, right? 100 product in a warehouse waiting to be inspected, and 10 of the products are defective. Okay, so there are 100, 10 of them are defective, so they are mixing up. You don't know which one is defective, which one is not. So here is the big picture. We have 100 products, and then 10 of them are defective. Actually, we don't really need a picture, so just have 100 products. So actually, you know what? Here. You know what? 10 defective, 90, they are not defective. So the total is equals to 100. Huh? That works. If one product is selected randomly, what is the probability that the first product is defective? So A, probability, first defective, the first product is defective. So the total frequency is 100, right? How many defective products are there? There are 10. Then there you go. Or you can simply reduce the fraction to 1/10. Divide the top and bottom by 10. And then B, without replacing the first product back to the pile, what is the probability the second selected product is defective? So given I already know that the first one is defective, what is the probability that the second selection is defective, but you don't put the first one back to the pile? So that affects the total, right? So it was supposed to be 100. If you don't put it back, then you have to subtract 1 because you are holding the first one. That changes the total frequency. You have to do 100 minus 1, and then the first one is defective. I just found it. I am holding that on my hand. So the number of defective in the pile right now is no longer 10. That is a 10 minus 1. So that is equals to 9 divided by 99. So are they independent? The answer is no, they are not independent. So these two events, they are dependent, because this probability affects this probability. The first result affects the second result. They are dependent. So that one I just answered C. Based on A and B, what is the probability of selecting two defective products? So the first one is defective, the second one is defective, right? So D. So probability first defective and second defective. So here I would like to recall a formula. So A and B, so remember this. The probability of A given B, that is equals to the probability of A and B divided by the probability of B, right? So if you multiply probability on both B on both sides, so that means you have A given B times B equals to A and B, right? So you are looking for A and B. This is the one that you are looking for. So that means you are looking for the first defective. Actually, this one you can switch them. This one you can switch them second defective given the first defective multiply the probability of first defective. If you want to make that change, I can change this one to a B and A. So that is B and A divided by A. So this will be multiply A on both sides. So that will be B divided by A. So that is equals to B and A. And then this is, because the first and the second, you can simply put that as second and first. The N, you can easily interchange these two events. That doesn't affect anything. So that will be B and that will be A. So this will be B given A multiply and then BA, right? So this one is right here. And then we complete the math. So the conditional probability is 9 divided by 99. And then this one is 1 divided by 10. So the probability is 9 times 1 is 9. 99 times 10 is 990. So that is the probability that we are looking for. And then that is the end of this video. If you think my instruction is helpful, please like, share, and subscribe. I appreciate your help really, really much. I will see you all in the next lesson. Signing out.